There's some basic terms and parameters used to analyze heat exchanger performance. And here we're going to talk about two of those. One of those is the number of transfer units, often called NTU, which is a measure of the size of the heat exchanger. And the other is the heat exchanger effectiveness, epsilon. Epsilon is actually given more straightforwardly as the total amount of heat transfer between the cold fluid and the hot fluid divided by the maximum theoretical amount of exchange that could occur. And so let's just talk about this for the problem that we've looked at for the condensing heat exchanger problem. For the condensing heat exchanger problem, if you recall, we said that there is a two-fluid problem in which there's a hot condensing fluid on the shell side and a cold fluid in the tube side, which is heated up by this shell flow. So we have this hot, saturated fluid that is the shell side fluid. It goes in at T saturated, it comes out at T saturated. There's a phase change process occurring. And then we have this cold fluid that comes in at TC in and leaves at TC out. From the simple differential equation that we derived, we came up with the fact that the temperature distribution has this exponential form. Recall that that differential equation basically said that in terms of an excess temperature, d theta dx is equal to minus up over m dot c theta, where again theta was equal to Tc minus Tsat. So using that, we came up with this. So I hope you recognize that the units of UPL over m dot specific times the specific heat is dimensionless. So all the arguments of this exponential have to be dimensionless. And so this NTU, this number of transfer units, oftentimes also thought of as U times the area divided by m dot C is also dimensionless. That's a dimensionless parameter, but it gives us an idea about the size of the heat exchanger. So sort of more straightforwardly understand what this epsilon parameter is and how epsilon can be thought of in terms of this NTU parameter. Let's just do a little bit of algebra. So if we claim that epsilon is equal to the heat transfer rate divided by the maximum heat transfer rate, it makes us think a little bit about what we might mean by the maximum heat transfer rate. So for a problem of this type, the maximum heat transfer rate is the heat transfer rate that would occur if we had the mass flow rate of that cold fluid times its heat capacity times now the temperature difference between the maximum temperature that this fluid can reach is Tsat minus what it came in at, which is this Tc in. So that defines really the maximum possible temperature or maximum possible temperature that the cold fluid would reach and the maximum heat transfer rate that could occur. The actual heat transfer rate that occurs is the mass flow rate. So this is using sort of the global temperature, global energy balance, and it would be the temperature of the cold fluid at L minus its inlet value. So this TL is Tc out. So that's the real heat transfer rate. But we have an expression for TL minus Tc in. So first thing we can do is we can certainly cancel out these guys. So we know that TL minus Tsat is equal to this Tc in minus Tsat times the exponential of minus NTU. And that's the UPL over m dot c. And so you see pretty easily that if we subtract off TCN from this, and we add Tsat to the other side, then we'd have plus TCN minus Tsat times exponential of minus NTU. And we can change this pretty easily. Tsat minus TCN minus Tsat minus TCN exponential minus NTU. So what this says, let's just make sure this is clear. What this says is that epsilon is simply equal to, so let's just substitute it just to make sure that it's absolutely clear. So we cancel all these factors out, and we see it's equal to 1 minus epsilon e to the minus NTU. Now, this is not generally true. What is generally true is that epsilon is a function of NTU and is a function of the ratio of the specific heat capacity times mass, which is sometimes called this capacity ratio. So it's a ratio of m dot C of the cold stream over m dot C of the hot stream, or sort of the reverse of that. So it's a ratio of the heat capacities of the two streams in general. And we're going to see how to use this in terms of understanding problems involving these heat exchanger systems.